Hello everybody, and it's time for video 4 of module number 6, our last video for module 6, where we will talk about the very exciting and interesting atmosphere of Venus. Of all the terrestrial planets, this is the thickest atmosphere, and we'll talk about its structure. We will talk about some interesting features, this layer of winds high in the atmosphere that are super rotating winds. They rotate around the planet at very, very, very high speeds. We'll talk about the composition of Venus's atmosphere, which gives us its extreme greenhouse effect, giving it the highest surface temperature of all the planets. And then we have to talk about why Venus is the way it is. Why is Venus's atmosphere different than Earth's atmosphere? Why is it so thick, and why is it such a hellish planet that is a CO2 rich atmosphere? Let's go ahead and dive right in. Up here we have a artist's impression of what it might be like to be flying through the skies of Venus. Not a very, very pretty view. And as always, anytime that we're going to be talking about a atmosphere of a planet, we're going to take a look at our temperature here on the x-axis versus the altitude, so how high up going towards space, which you could also map that by pressure. Let's first go ahead, remind ourselves that Venus has the thickest atmosphere of all of the terrestrial planet atmospheres. So its surface pressure is 90 times that of Earth's. Its mass, the total mass, the amount of stuff that the atmosphere is made up of, is about 93 times more massive than Earth's atmosphere, 90 times the surface pressure. At a surface pressure that high, that's about the equivalent pressure you would experience if you were to dive down into an ocean and swim down a kilometer. Submarines have a hard time diving down that deep because that pressure is so enormous, which translates to how I like to describe the surface pressure on Venus. It's enough where if you're on the surface of Venus, it would squish you flat like a pancake. So much pressure pushing down on you would destroy you, it would squish you flat. So a very, very, very thick atmosphere, and it being so thick and so massive, it means it's a very extended atmosphere as well. So remember, the Earth's troposphere was in the first 10 kilometers. The top of Earth's atmosphere was at 100 kilometers. And really, the top of the troposphere for Venus extends up to about 100 kilometers. So all of Earth's atmosphere could fit in Venus's troposphere. What makes it the troposphere is where the weather is occurring. It's where convection is occurring in the atmosphere. It's where, as you go higher in altitude, you have lower and lower and lower temperature. Then you have that temperature inflection point. As you go higher, then you call this perhaps the stratosphere of Venus, where our pressures are pretty low. So the troposphere tops out at about 100 atmosphere. And since all the weather occurs, pretty much all the weather occurs there, all the clouds of Venus are in there. So those highly reflective clouds that are blocking our view of the surface of Venus in visible light, they hang out at about 50 to 70 kilometers above the surface. And clouds are very, very reflective, right? They're white and bright in the sky, which means that Venus is going to end up with an albedo of 0.7. So 70% of the sunlight that comes in hits these clouds and reflects back, and only 30% will go into the planet. So it has a very, very, very high albedo of 0.7, which allows it to be so bright in the sky. It's very, very close. It's a pretty big planet, the second biggest terrestrial planet, and it's very reflective with an albedo of 0.7. Okay, so here we have above a lot of the reflective clouds, so cool things that are going on, or hellacious things if you want to go with that way. You have sulfuric acid clouds. So you have thick clouds of sulfuric acid, sounds lovely. And then if you can clear the sulfuric acid clouds, you have a haze of sulfuric acid. So joy, if you did not enjoy going through clouds of sulfuric acid, we all enjoy going through a smog of sulfuric acid. So not a very safe environment to be going in. And so you're talking about going through sulfuric acid at temperatures that are deadly. So this is why I was saying that a good representation of the biblical hell might be Venus. Sulfuric acid clouds, surface temperatures up at about 800 Kelvin or so, over 800 degrees Fahrenheit, hot enough to melt lead. So a not very pleasant atmosphere. And it also has some other interesting things. So if we go to that highly reflective cloud layer that's obscuring our view, the one that's giving it that high albedo, right above those clouds, we have what are called super rotating winds. So remember, Venus rotates very, very slowly, once every 243 days. However, the atmosphere up there is rotating around Venus once every several days. So above the clouds, there's a very, very high speed traveling west to east, westward winds uh, that form sort of a jet stream. So super, super, super high speeds, about 90 meters per second. That's about 200 miles per hour, about 300 to 400 kilometers per hour. Winds that are just ripping around the planet. They go about 10 degrees in 4 hours. You can go ahead and do the math to figure out how many days that would be. And whenever you have these winds that are literally circling around the planet much, much, much faster than the rotation rate, then we call such things super rotating winds. So Venus has super rotating winds high up in the atmosphere, which, if you think about it, that makes it kind of hard to descend through a layer where you have winds that are as fast as hurricane or faster than hurricane winds. Once you get through that, and then you go through your sulfuric acid clouds and the sulfuric acid haze down into the clear skies at the bottom of the troposphere, by the time you get to the bottom, that nice thick 90 atmospheres of pressure, the air is kind of soupy, and that might be the best way to describe it, is at that pressure, the air is going to behave more like ocean currents or water almost, although it's still a gas. So the very, very gentle, sluggish 4 mile per hour winds occur at the surface, but they behave more like ocean currents. And I just saw this absolutely amazing graphic from the Akatsuki team, the JAXA team, the Planet C team, where you can actually see the super rotating winds right there. This is an infrared image. You can see them actually moving. This is a series of images over time. This is the night side of Venus, so you can actually use infrared to see structure in the clouds. This is the day side of Venus, where everything is just way too bright, so you can't really see anything. We're looking at 2.26 microns for the curious. And with this, you can see that the winds are blowing, moving at about 10 degrees every 4 hours, or about 2.5 degrees per hour. So, crazy atmosphere. We know a little bit about its structure now. What is it made out of? So we can go ahead and take a look at its atmosphere, and I try to put it in sort of a bar graph here, just to really accentuate that. For the thickest atmosphere, 93 times the mass of Earth's atmosphere, 96.5% of all the atmospheric gases, the most abundant atmospheric gas, is carbon dioxide. So almost all of Venus's atmosphere is carbon dioxide gas. What's expected from what we would assume a secondary atmosphere to be like, just minus all the water, because it has almost no water at all. Remember, Earth had a pretty variable amount of water. Okay, so almost entirely carbon dioxide, 96.5%. What's gas number 2, the second most abundant one? Nitrogen, N2, which is Earth's most abundant gas. At 78% of Earth's atmosphere, only 3.5% of Venus's atmosphere. But this is to be expected, because that same photodissociation event that built up into an Earth's atmosphere should have been going on in Venus's atmosphere. Venus just didn't get rid of all the CO2 by dissolving in the oceans and locking into the surface rocks. So it has nitrogen as number 2, but it still has all that CO2 in its atmosphere. And then what's the third one? Well, I guess that's sulfur dioxide. And then you have argon as well, which is something that you would expect. How do we know all this? How do we know the atmosphere of Venus so well? Well, one, we can use spectroscopy. So here we're just looking at wavelength in the infrared versus how bright, and we can see these absorption bands due to carbon dioxide, things like that. So we can use spectroscopy to get it, but we also had the USSR's Venera probes that descended through the atmosphere, taking atmospheric measurements the whole way down. So yes, we know the composition of Venus's atmosphere quite well. And with such a thick atmosphere, 93 times the mass of Earth's atmosphere, 96.5% of all of that gas being carbon dioxide being a greenhouse gas, you might expect Venus to have a pretty insane greenhouse effect. And we can really see that by going back and asking our question, what temperature do we expect Venus to be? So, how hot should it be? What is its expected temperature? What is its equilibrium temperature? So based on its distance from the sun, about 0.7 AU, and its high albedo, about 0.7, reflects 70% of sunlight, you can go ahead and do the calculation, and you'd expect Venus to have an average surface temperature of 260 Kelvin, just a little bit warmer than Earth's. Still below the freezing point of water. Why is Venus so hot, though? Why is the surface hot enough to melt lead? And it has an extreme greenhouse effect. 96.5% of the atmosphere is carbon dioxide, a strong greenhouse gas. It's very good at absorbing outward bound infrared radiation, and then whenever it re-releases it, you can either go spaceward or back down. And with such a thin atmosphere, what's going up is probably going to run into some more CO2. So the net effect is 99% of all the infrared radiation the planet is trying to send to outer space. Only 1% gets back out. 99% goes back into the surface. That is an extreme greenhouse effect of plus 480 Kelvin, raising the surface temperature to past balmy to just a straight up inferno of 740 Kelvin. Hot enough to melt lead. The thick atmosphere also regulates this temperature planet-wide. Since the atmosphere is so thick, doesn't matter on the surface or you're on the day side or the night side, at the poles or the equator. It's pretty much the same temperature all day, every day on Venus, and it's stupid hot. Now, why is Venus's atmosphere so different than ours? If we are sister planets, twin planets, why are we so different? And perhaps the question isn't what's weird about Venus's atmosphere? Perhaps the real question is what's weird about Earth's atmosphere? What happened with Earth's atmosphere that didn't happen with Venus? Or what effect happens on planets that will eventually happen on Earth, giving us a very Venus-like atmosphere? And for this, we have to study and go over what's called the runaway greenhouse effect. And spoiler alert, this will play out on Earth. The same process is coming in roughly 1 to 1.5 billion years here on Earth. Notice that's a huge time scale. So this is not climate change. Well, this is not anthropogenic climate change. This is just what will happen in the future in about 1 to 1.5 billion years. All right, let's go to the starting point. We form Venus, we form Earth, they lose their primary atmospheres, they volcanically outgas their secondary atmospheres, which are enriched with things like carbon dioxide. This is what we expect, sulfur dioxide, water vapor, things like that. So Venus has what we expect from a secondary atmosphere. Earth does not. What is the difference? Venus experienced what we call the runaway greenhouse effect. Why did this happen on Venus already and not on Earth? Why do we have to wait 1.5 billion years on Earth? Most likely, it's as simple as the Venus formed just a little bit closer to the sun at 0.7 AU instead of 1 AU away. So let's walk through this. The steps of the runaway greenhouse effect. Let's start with an early Venus. Let's assume a Earth-like starting point. So just by how secondary atmospheres form, something that we've studied in general for terrestrial planets, and evidence that we can gather, especially about how much water is leaking out of the top of Venus's atmosphere, we can backtrack, and not all that long ago, or actually very long ago, but For perhaps the first 2 billion years or so, Venus should have been able to support liquid water as an ocean on its surface. And being made out of the same kind of stuff, the same processes happening to it, you just expect Venus to have about the same total amount of water early on as Earth would have had. So very likely the early Venus was very Earth-like, where as the atmosphere cooled, the water formed oceans, sucked out the CO2, locked it into surface rocks, and perhaps for the first 2 billion years or so, Venus was a very habitable world. Perhaps life even evolved. But it's closer to the sun. And the sun is slowly, ever so slowly, becoming brighter. It's increasing solar luminosity. Its amount of energy it's giving off per square meter is increasing. Why? Well, as stars age, they fuse. How are they powering themselves? They fuse hydrogen to helium, making them shine, and they make more and more helium. And it builds up in the core. Helium is more massive, more dense, so that core contracts under gravity as that helium builds up, which drives up temperatures, which drives up the fusion reaction rates, which overall increases the luminosity of the sun very, 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 very slowly. So at the formation of Earth and Venus, at the start of the solar system, the sun would have only been about 70% as bright as it is now. Very, very, very slow effect. Please see the supplemental slide. This is not a forcing factor in climate change. So this is a change of less than 2 times 10 to the negative fifth watts per meter squared since the Industrial Revolution. And you have to remember that climate change, we're talking about several watts per meter squared. So we are talking at least about 7 or more, well, 6 or 7 orders of magnitude less of an effect. So negligible is an easy way to put it. But Venus, being closer to the sun, would have been more susceptible to these changes earlier on. And this would have started the runaway greenhouse effect. As the sun brightened, Venus's average surface temperature would have gone up and up and up and up and up. And eventually it would have gotten high enough so that the oceans would start to evaporate. And when the oceans evaporate, it's putting water vapor, a greenhouse gas, and carbon dioxide into the Venusian atmosphere. So we're going to kick off a runaway process here. The sun increases in brightness, which starts to evaporate the oceans. The evaporating oceans put carbon dioxide and water vapor into the atmosphere, both greenhouse gases. More greenhouse gases in the atmosphere means increasing the greenhouse effect. So the planet gets hotter, has a higher surface temperature. We have an increased greenhouse effect. We're just going to start evaporating the oceans faster, putting more of the trapped CO2 and more water vapor up into the atmosphere. So the planet's going to get hotter, which is going to cause the oceans to rapidly evaporate in this feedback loop, putting all of that locked CO2 and all the water that was in liquid form into the atmosphere. So this is how the process runs away. The water will end up getting photodissociated, split into oxygen and hydrogen. The hydrogen will float away, never to return. So over time, we lose all the water, and we just end up with a CO2-rich atmosphere. So this runaway greenhouse effect, the end result is you end up with a very, very, very thick atmosphere that's composed almost entirely of carbon dioxide. So now consider the future Earth. You don't necessarily need to know this, but I always find it a fascinating thing to go through. I hope it doesn't ruin anybody's day. But due to the fact that how the sun is brightening, this fusion of hydrogen to helium in the core of the sun is still continuing to happen. So the sun is continuing to become brighter with time. So slowly, over hundreds upon hundreds of millions of years, it'll be noticeably brighter. So that in roughly 1 to 1.5 billion years, the sun will be bright enough to raise the Earth's solar constant enough to trigger the runaway greenhouse effect, where our oceans will start to evaporate, thus putting the water vapor and the locked CO2 back into our atmosphere, kicking off the runaway greenhouse effect until it reaches its natural conclusion. And at that point, all that locked CO2 will be put back into Earth's atmosphere, and Earth's atmospheric composition will be expected to be about 98% carbon dioxide and 2% nitrogen, and about 70 times more massive than it currently is. That sounds very, very, very Venus-like. And of course, if we're very Venus-like, our greenhouse effect will be super high, our surface temperatures will be super hot, we don't breathe carbon dioxide. So this will spell the end of all life on Earth. And out of all the doomsday extinction topics that we've talked about in astronomy in this class so far, this one is it. This is the one that has the highest certainty that will end life on Earth. It's unavoidable without some severe technological things that could really, really like globally alter and terraform Earth to prevent this from happening. Hope it's not real. Hope it doesn't ruin your mood for the end of the semester. That's kind of an interesting thing to have in your back pocket, that you actually know what the right doomsday extinction event's not going to be the giant asteroid. Could be, but I mean, that's a probability thing. It's the eventual runaway greenhouse effect in about 1.5 billion years. And on that glorious and uplifting note, sarcasm, in case it didn't come across, I'm going to go ahead and end lecture module 6. I hope you enjoyed tuning in. And we will pick up next time with